Bismillahirrahmanirrahim. Up to lecture number 18, we have discussed conduction and radiation. In our first lecture, we have discussed that there are three modes of heat transfer: conduction, convection, and radiation. We have discussed conduction, we have discussed radiation. Now, in lecture number 19, we are going to start the third heat transfer mode, which is known as convection. And this lecture we will discuss about the fundamentals of convection. We will discuss about the velocity and thermal boundary layer. We will discuss about the local and average heat transfer coefficient, and we will discuss about the dimensionless parameters. So according to introduction, we have discussed there are basically three modes of heat transfer: conduction, convection, and radiation. Conduction and convection are both similar as they require material medium. We have seen in conduction that conduction requires a material medium, and we have seen in radiation that there is no material required in medium. Medium can occur without a medium, it can occur in a vacuum, and similarly convection requires a material medium. Because if you remember first lecture in which we have seen videos related to conduction, convection, radiation, in convection there is a requirement of fluid, and we all know that fluid is a material, so convection also require a material medium. And conduction and convection both are similar, that they require material medium, but they are different, that convection requires a presence of fluid. Consider this picture, and this is the pink plate is heated at a temperature of 50 degrees centigrade, and a fan is forcing air on it with a velocity of 5 meters per second, and the air temperature is 20 degrees centigrade. So it means that the temperature gradient exists between air and this plate, so it is obvious that heat transfer will occur. As the air of 20 degrees centigrade will pass over this flat plate, heat transfer will take place, as this plate is at a temperature of 50 degrees centigrade. So heat will flow from this plate to the air, and since we are forcing air on it, that's why it is written here forced convection. We are forcing air on it through a fan, that's why it is written forced convection. If there is free convection without inclusions of any external device, then there will be a free convection, and if there is no convection current, then there will be no convection. The heat transfer will be purely conduction if there is no convection. So convection is basically the conduction plus bulk fluid motion. Heat transfer through convection will occur when there is a conduction plus bulk fluid motion. If there is a fluid in motion, then the heat transfer mode will be convection, not conduction. And convection consists of conduction plus bulk fluid motion, which is also known as advection. So in conduction, heat transfer occurs from a solid to the fluid due to bulk fluid motion. Whenever there is a bulk fluid motion and the temperature gradient exists, the heat transfer mode will be convection. So in fluid, conduction may be viewed as a limiting case of convection. Here the last point, conduction in a fluid can be viewed as a limiting case of convection corresponding to the case of quiescent fluid. Means that in fluid, conduction is the limiting case of convection if there is no fluid motion. If there is no fluid motion, then the heat transfer mode will be conduction, not convection. You will see that it is possible that in fluid there is no fluid motion but heat transfer is taking place. It is actual happened that there is no convection current, and if there is no convection current, then the heat transfer mode will be entirely conduction, not convection. So the presence of fluid does not mean that the heat transfer mode is purely convection. Convection will occur only when there is a bulk fluid motion. When there is a fluid in motion, then heat transfer mode will be convection. If there is no fluid in motion, then the heat transfer mode will be conduction. So I hope this will give you a clear understanding of the convection. And now we are looking at a concept which you have learned in fluid mechanics too, that this is the plate and flat plate, and the free stream of air with velocity u infinity is approaching towards 8, and this fluid will form a boundary layer, and outside the boundary layer the velocity will be same as that of free stream u infinity, and inside the boundary layer u will vary with the thickness of the boundary layer. It is evident from this picture that the fluid layer which is near the plate will at a low velocity than the layer of a fluid at a distance from it, and the fluid layer which is in contact with the plate will have a zero velocity, no slip motion, and the velocity will gradually increasing as you move towards the boundary layer thickness. It forms a boundary layer, and you have learned in fluid mechanics that boundary layer is a thickness of the fluid where velocity is 99% of the free stream velocity. Near the plate the fluid velocity will be 0. The point where the fluid and plate are in contact, the velocity will be 0, and velocity will increase if you move upward. So it means that velocity is a function of y. If I took this direction in which my cursor is moving, which is the vertical direction, as y, and this horizontal direction as x, so it means that within the boundary layer velocity is a function of y, because velocity is changing in y direction. Within the boundary layer, the point where fluid is in contact with the plate, the velocity is 0, and at a certain height the velocity becomes equal to 99% of the free stream velocity, and outside that limit velocity is the free stream velocity. So I hope this concept you have learned in fluid mechanics, which is known as boundary layer concept. So this is the velocity boundary layer. You have learned velocity boundary layer, you just focus on the velocity. So this is basically the diagram. This is the free stream velocity approaching towards the flat plate. This direction is taken as x, and this vertical direction is taken as y, and thickness is formed, layer is formed, which is known as velocity boundary layer, in which the viscous effects are significant. Within the boundary layer viscous effects are significant, and outside the boundary layer viscous effects are negligible. So the fluid particle which are in contact with the plate have a 0 velocity, and velocity will gradually increase if you move towards the top, and there exists a point where velocity becomes equal to 99% of the free stream velocity, and that point where this occur, here it is written that u is equals to 0.99 of u infinity. It means that the point where velocity of the fluid becomes equal to the 99% of the free stream velocity, that thickness, that limit is termed as boundary layer thickness, denoted by delta, and the quantity delta is termed as the boundary layer thickness, and it is typically defined as the value of y for which u is equal to 0.99 of u infinity. Means if you move in y direction, a point where the velocity becomes equal to 99% of the free stream velocity, that point is known as boundary layer thickness. Within the boundary layer, the velocity of a fluid is the function of y, and outside the boundary layer the velocity is the free stream velocity. For external flows, it is used to measure the CF, which is known as frictional drag coefficient, and which is the dimensionless parameter from which we can determine the frictional drag. And here tau s is the shear stress, and it can be evaluated from the knowledge of velocity profile. Here dava u over dava y is the change of velocity with respect to y, and mu is the viscosity of the fluid. And I have mentioned that velocity boundary layer is a region in which friction effects are significant. Outside the boundary layer, friction effects are negligible, but within the boundary layer, friction effects are significant. As you have learned the concept of boundary layer, velocity boundary layer, similar concept exists for thermal boundary layer. As within the boundary layer, velocity is a function of y, and there's a point where velocity becomes equal to 99% of the free stream velocity, and that point, that value of y is known as the boundary layer thickness. Similar concept is available for thermal boundary layer. So we are moving towards the thermal boundary layer using the concept of velocity boundary layer. Now consider this is the flat plate which is maintained at a temperature Ts, and the temperature Ts is higher than the free stream temperature T infinity. Consider this is a flat plate and it is maintained at a temperature Ts, and a fluid with a velocity of u infinity and temperature T infinity is approaching towards it. There will form a boundary layer, and the thickness for thermal boundary layer known as the thermal boundary layer thickness. Now the fluid which is in contact with the fluid which comes in contact with this fluid, the layer of the fluid which comes in contact with this fluid will be at the same temperature of Ts, and it will gradually decrease if you move in the y direction. For example, like this profile, this T profile, the layer of the fluid which comes in contact with the surface having temperature Ts will have the same temperature of Ts, and if you move in y direction it will gradually decrease. So it means that within the thermal boundary layer, temperature of the fluid is a function of y, and at leading edge means the point where fluid start approaching towards the plate. This point is known as the leading edge. At leading edge, T of y is constant, it is not changing, but beyond leading edge there forms a thermal boundary layer, and within the thermal boundary layer temperature changes with y. So there is a definition for thermal boundary layer thickness, and remember thermal boundary layer thickness is denoted by delta T, and it is the value of y for which Ts minus T over Ts minus T infinity is equal to 0.99. It means the difference of temperature between air and the surface becomes equal to 99% of the temperature difference between surface and the free stream velocity. So delta T, the thermal boundary layer thickness, is the value of y for which Ts minus T over Ts minus T infinity is equal to 0.99. And if you want to take a heat flux at any location within this boundary layer, at any location at a distance x from this leading edge, you can apply Fourier's law of heat transfer, because the point where the fluid comes in contact with the surface. For example, this one is the point where the fluid comes in contact with this surface. Here the fluid will have a zero velocity, as we have seen in velocity boundary layer thickness. The point where fluid comes in contact with the surface, at that point the fluid will have a zero velocity. Zero velocity means at that point there will be no fluid motion. Zero velocity means there is no fluid motion. So at that point there is no fluid motion. It means the heat transfer will be due to conduction, not convection. So at any point at a distance of x from the leading edge, local surface heat flux may be obtained by applying Fourier's law to a fluid at y is equals to 0. So we can apply Fourier's law of heat transfer, which will be Qs double H is equal to minus k dou T over dou y times y is equals to 0, because y is T is changing in y direction. That's why we have taken temperature gradient in y direction. And remember that temperature is changing in y direction, and the point where fluid comes in contact with the surface will have a zero velocity, and due to zero velocity there will be no fluid motion, and no fluid motion means the heat transfer will be due to conduction at that point, and beyond that point heat transfer will be due to conduction. So at y is equals to 0, heat transfer is purely due to conduction, and we can apply Fourier's law of heat transfer in order to determine the local surface heat flux, which will be equal to Qs double dash is equal to minus k dou T over dou y at y is equal to 0. Now carefully look, that heat flux will be transferred to the adjacent layer of the fluid. For example, this one is the surface layer of the fluid which is in contact with the surface. This one is the second layer of the fluid. This one is the third layer of the surface, fourth, fifth, sixth, and so on. So the heat flux which passed into the first layer will then transfer to the adjacent layer. So we can write that beyond first layer heat transfer is occurring due to convection. So we can apply Newton's law of cooling at that point, and which will be Q double dash S is equal to H Ts minus T infinity, because this one is the heat transfer to the fluid layers which are not in contact with the surface. So we can apply Newton's law of cooling, and we can compare Fourier's law of heat transfer and Newton's law of cooling, because first heat will transfer due to conduction and then convection will occur. So we can compare both, and we can write H is equal to minus k dou T over dou y at y is equals to 0, Ts minus T infinity. So it means that if you know the temperature profile within the thermal boundary layer, and you know the fluid properties, you can measure the free stream temperature, you can measure the surface temperature, you can easily determine heat transfer coefficient, convection heat transfer coefficient, if you know the temperature profile. Only one thing you require, which is the temperature profile. So if you know temperature profile within the thermal boundary layer, then you can calculate convective heat transfer coefficient, because K is the fluid property, it is the it is the thermal conductivity, and it is the material property. Ts and T infinity can be measured by using any temperature measurement device. T infinity is the free stream temperature, and Ts is the temperature of the surface. So if you know just temperature profile, you can easily determine convective heat transfer coefficient. Keep remember this equation in your mind. I would recommend you to pause my video here and write this equation at your notebook. Now we are moving towards boundary layer equations. Velocity boundary layer you have discussed in your fluid mechanics course, and it requires a conservation of mass for a steady process, two-dimensional problem. The conservation of mass continuity equation comes equal to dou u over dou x plus dou v over dou y is equal to 0. This is the continuity equation for two-dimensional steady state problem. And conservation of momentum will be u dou u over dou x plus nu dou u over dou y plus nu dou y square u over dou y square. These two equations you have learned in your previous fluid mechanics 2 course, and you have also learned that velocity boundary layer thickness is equal to delta over x 5 upon Reynolds number power x, which is the exact solution of the boundary layer thickness. And if you want to approximate the boundary layer thickness, then it will be delta over x is equal to 4.64 upon Reynolds number power x, Reynolds number power 1 upon 2. These two boundary layers equations you have learned in your fluid mechanics course. And velocity profile will be u upon u infinity is equal to 3 upon 2 y upon delta minus 1 upon 2 y upon delta power cube. These equations I hope that you have learned in FM fluid mechanics, so we are not going in detail of these equations. As you have velocity distribution, we have seen that temperature profile boundary layer, thermal boundary layer is analogous to the velocity boundary layer. So temperature distribution will be analogous to this velocity distribution, and it will be T minus Ts upon T infinity minus Ts is equals to 3 upon 2 y upon delta T minus half y upon delta T power cube. Here T is the temperature of the fluid within the boundary layer, Ts is the surface temperature, T infinity is the free stream temperature, delta T is the thickness of the thermal boundary layer, and y is at any distance within the boundary layer. So I hope that you have learned velocity distribution in fluid mechanics, and from the same concept we have developed the temperature distribution, and temperature distribution is analogous to the velocity distribution, and it is written on your screen. Here I will again recommend you to pause my video and write the temperature distribution, all these equations on your textbook. Now we have learned conservation of mass, we have learned conservation of momentum, we have learned velocity boundary layer thickness, we have determined velocity distribution. All these equations we have learned in fluid mechanics, and temperature distribution is analogous to the velocity distribution. Now we are moving towards the another equation which is related to the thermal boundary layer, and that equation is known as energy equation. So we are considering this differential volume within this boundary layer. Consider this differential volume in the boundary layer. So draw this differential volume at your notebook. We have taken this differential control volume, and this is the energy in due to advection, means due to flow of fluid, and these two are the energy in due to conduction as well as due to advection. This one is the energy out due to advection, this one is the energy out due to advection, and this one is the energy out due to conduction. In order to we will learn all these energy in and out in this slide, but in order to drive the thermal boundary layer equation, we have assumed that our flow is incompressible, we have a steady state condition, we have assumed fluid properties are constant, and there is negligible heat conduction in the flow direction. Means this green arrow shows the fluid motion. Fluid is moving in x direction, so there is negligible heat conduction. Conductive heat transfer in the flow direction is negligible, and we have assumed that velocity boundary layer thickness is greater than the thermal boundary layer thickness. Now These are the energy in and out of this differential volume. The green one is the energy in due to advection, which is the mc m dot cpt, and we have know that mass flow rate is equal to rho av. So we have rho, we have u. Rho is the fluid density, u is the velocity in x direction, and if we have assumed a unit depth, so area will be dy into 1 or simply dy. So m dot will be rho u dy, and cp is the specific heat at constant pressure, and T is the temperature. So the amount of energy in from this phase will be rho Cp ut dy, and the amount of energy that goes out from this direction will be this energy plus change of this energy with respect to x. The energy that goes out from the right phase, this light blue arrow shows the rate of energy that advected out of the right phase, and it is rho Cp ut plus dou over dou x ut dx times dy. Here within this control volume, as you move in x direction, so it is obvious that this energy in will get changed with respect to x. So the amount of energy that goes out of the right phase will be rho Cp ut plus dou over dou x plus ut dx times dy. Now we are moving towards this arrow, the orange one. It is the amount of heat advected into the bottom phase, and it is rho Cp Vt dx. Rho is the fluid density, Cp is the specific heat at constant pressure, T is the temperature, and V is the velocity in y direction. And if you take unit depth, so area will be dx into 1, and it will be simply dx. So the amount of energy that advected into the bottom phase will be rho Cp Vt dx. Now this energy will get advected out from the top phase, and it will change with respect to y, because we are moving in y direction, so this energy will get changed with respect to y. So the amount of energy that goes out of the top phase will be rho Cp Vt plus dou over dou y Vt dy into dx. Now we have assumed that heat transfer due to conduction is negligible in flow direction, and fluid is flowing only in x direction. So we will take conduction in y direction. This purple arrow shows the rate of conduction into the bottom phase, and it will be minus k dou t over dou y times dx, and the rate at which energy goes out of the top phase will be minus k dou t over dou y plus dou y square t over dou y square times dx, because the area perpendicular to this energy flow is dx into 1 or simply dx. Now if we consider the viscous forces, then there will be work done on this control volume due to viscous forces, and which will be equal to tau dx dou u over dou y dy, which will be equal to mu dou u over dou y square times dx dy. So basically there are 7 energy in and out, 7 equations. Equation 1, 3, 5 and 7 shows the energy in on this control volume. Equation 1, which is written at top, equation 1, 3, 5 and 7 shows the energy that comes in of this control volume, and the equation 2, 4 and 6 shows the energy that goes out from this control volume. So in order to justify the energy balance, energy in will be equal to energy out. So if we are going to apply energy balance, equation 1 plus 3 plus 5 plus 7 will be equal to 2 plus 4 plus 6. It means the energy that comes in will be equal to the energy that goes out. So we have this equation. We have just put all the equation, and we have arranged the equation, the in equation on the left hand side and the out equation at the right hand side. After this simplification, we have k dou y square t over dou y square dx dy plus mu dou u square dou by dou y whole square dx dy is equals to this. We, after the simplification, we have this equation. You can simplify this equation by yourself on your notebook. I would recommend you to move towards this, solve the equation, which is multicolored equation, and then drive this equation, and you can further cancel dx dy from both sides by taking common out. And here what we have did, that we have taken raw CP out of this large bracket, and we have taken the velocity velocity gradient and temperature gradient separately. Here this is the temperature gradient, so we have taken temperature gradient. Here this is the velocity gradient, so we have separated velocity gradient. So we have just separated velocity gradient and temperature gradient. Now closely look at this bracket, dou u or dou x plus dou v over dou y. My cursor is pointing. What it is written, this is the continuity equation in 2 dimension for steady state case. So dou u or dou x plus dou v over dou y is equal to 0, because this is the continuity equation. So when we put 0 in this equation, this term will be get cancelled. We have simplified equation k dou y square t over dou y square plus mu dou u over dou y whole square is equals to raw cp u dou t over dou x plus v dou t over dou y. And by just dividing whole equation by raw cp, we have u dou t over dou x plus v dou t over dou y is equals to alpha dou y square t over dou y square plus mu over raw cp dou u over dou y. When you divide k by raw cp, it will become thermal diffusivity. Go back to chapter number 2, in which we have learned thermal diffusivity, and thermal diffusivity is equal to k over raw cp. That's why we have written here alpha. So we have equation, simplified equation, u dou t over dou x plus v dou t over dou y is equals to alpha dou y square t over dou y square plus mu over raw cp dou u over dou y square. This is the equation which takes viscous effects and viscous work into account. If there is negligible viscous work, then the last term, my cursor which is showing, will be get eliminated, and we have simplified equation if there is no viscous work, and it will be u dou t over dou x plus v dou t over dou y is equal to alpha dou y square t over dou y square. And this equation is known as the differential form of the boundary layer equation. This simplified equation is known as the differential form of the boundary layer energy equation. Now we are moving towards local and average convection coefficient. Consider a fluid with temperature T infinity and velocity u infinity is flowing over the isothermal plate, which is maintained at a temperature of Ts such that Ts is greater than T infinity. If Ts is greater than T infinity, then heat transfer will occur, and heat transfer will be in that direction, which is shown by this red arrow. If there is a temperature gradient exists, and if Ts is greater than T infinity, then this arrow shows the heat flux. Now the total heat transfer rate may be obtained by integrating the local heat flux over the entire surface. It means that if we know the heat flux at a point, then total heat flux will be determined by just integrating over the entire surface, and q dash will be Ts minus T h times Ts minus T infinity, and Ts minus T infinity is constant, so that's why we have taken Ts minus T infinity out of the integral sign, and we have just h das, And if we define the average convection coefficient, which will be Q is equals to H bar A S times Ts minus T infinity, then the average convection coefficient will be 1 over As integral H dAs. So if we know the local convection coefficient, then we can determine the average convection coefficient by just integrating over the entire surface. Local means at any point. If we know the heat transfer coefficient at any point, for example at this point, this dark dot, if we know the heat transfer coefficient at this point, we can determine the average heat transfer coefficient over the entire surface by just integrating it. So this is the equation which will be used in our convective heat transfer case. So I would recommend you to write this equation on your notebook. Now we are moving towards some dimensionless parameter which are very important in convection heat transfer coefficient. You have learned different dimensionless parameters in your fluid mechanics. You have learned, I hope you have learned Reynolds number, you have learned Mach number, and many other dimensionless parameter you have learned. Now we are moving towards the dimensionless parameter which are very useful in convective heat transfer. So the first dimensionless parameter is not new for you, and it is Reynolds number. And Reynolds number is the ratio of viscous force to the ratio of inertial forces to the viscous forces, and inertial forces increases with the momentum of the moving fluid, and this ratio is equal to rho VL over mu. I hope you have learned this Reynolds number in fluid mechanics, and Reynolds number is simply the ratio of inertial forces to the viscous forces. Rho VL shows the inertial forces and mu shows the viscous forces. So it is a ratio of inertial forces to the viscous forces. Reynolds number classify the laminar or turbulent flow. If we have large value of Reynolds number, it means that the flow is turbulent. If we have small values of Reynolds number, it means that we have laminar flow. For large values of Reynolds number, we have large inertial forces, it means it is turbulent flow. And for low Reynolds number means we have large viscous forces, it means that we have laminar flow. So Reynolds number is basically the ratio of inertia to the viscous forces, and it classifies either the flow is laminar or turbulent. Now we are moving towards another dimensionless parameter which is very important in heat transfer due to convection, and it is the Prandtl number, and is simply the ratio of kinematic viscosity, which is also known as momentum diffusivity, to the thermal diffusivity. It is the ratio of momentum diffusivity to the thermal diffusivity. Momentum diffusivity means kinematic viscosity, and thermal diffusivity both are the fluid property. Nu, which is the kinematic viscosity, is the fluid property. Alpha is also the fluid property. So Prandtl number is also a fluid property, and Prandtl number is simply Cp mu over K or nu over alpha. Prandtl number influences the relative growth of velocity and thermal boundary layer, and for laminar boundary layer it is reasonable to accept that delta over delta T is equal to Prandtl number power n, where n is any positive integer. So the ratio of velocity and thermal boundary layer is equal to Prandtl number power n, and for our case n is the positive integer, and for gases the thermal boundary layer thickness is approximately equal to the velocity boundary layer thickness. For liquid metal, thermal boundary layer is much more greater than the velocity boundary layer, and for an oil the thermal boundary layer thickness is very much less than the velocity boundary layer thickness. So Prandtl number is simply the ratio of kinematic viscosity to the thermal diffusivity, and it is a fluid property, and it provides a measure of relative effectiveness of the momentum and energy transport by diffusion. We have learned this in further lectures, that how it provides a measure of relative effectiveness of momentum and energy transport by diffusion. But remember, Prandtl number is simply the ratio of kinematic viscosity to the thermal diffusivity. Kinematic viscosity is also referred to as momentum diffusivity, and both momentum diffusivity and the thermal diffusivity are the fluid property. So Prandtl number is a fluid property, and it is equal to nu over alpha. Now we are moving towards one of the most important dimensionless parameter, which is the Nusselt number, and Nusselt number is simply the ratio of convection to the pure conduction, and it is simply Q convection over Q conduction. It means the heat transfer due to convection divided by heat transfer due to conduction, and this ratio is equal to HL over K. It is a function of Reynolds number and Prandtl number. This formula is exactly same as that of Biot number, but Biot number determines either the body is lump or not, and Biot number is the ratio of conductive resistance over convective resistance, but Nusselt number is the ratio of heat transfer due to convection to the pure conduction. So both Nusselt number and Biot number have the same formula, but both have different interpretation. Nusselt number is a ratio of convection to the conduction, and Biot number is a ratio of conductive resistance to the convective resistance. And this Nusselt number is used to determine the heat transfer convection coefficient, and this Nusselt number is exactly the same for boundary layer what friction coefficient is for velocity boundary layer. You know that what is the significance of friction coefficient for velocity boundary layer? The same significance is valid for Nusselt number if we talk about thermal boundary layer thickness. So remember, Nusselt number is a ratio of pure convection to the conduction, and it is equal to HL over K, and it is a function of Reynolds number and the Prandtl number. If we change the value of Reynolds number and Prandtl number, it means that we will get these change value of Nusselt number. Now with that, we have done with our lecture number 19. If you have any query, any question related to this lecture, you can ask on mail, in live session, on WhatsApp, and I would recommend you to note down all the equations, all the derivation on your notebook, if it will help you in understanding all these equations. So with that, we have done with our lecture number 19. So thank you.